Hi, and welcome to our next video in our series on trigonometry. And in this video, we're going to have a look at the trig curves, starting with y equals sine x. But what we're going to do is have a look at kind of sine x, cos x, tan x, have a good old play around with the curves, understand why you get the values that they do, and also look at values up to and beyond angles of over 360 degrees, and also what happens with negative angles as well. So here we go. Let's start off with y equals sine x. So to begin with, let's just consider a circle. So we've got a radius of 1 for our circle, and we know that for this triangle, sine theta is the opposite side over the hypotenuse. And so therefore what we get is sine theta is y, so there's my opposite over the hypotenuse. So we've got sine theta equals y over 1, which is just sine theta equals y. So what that's basically telling us is the height of the triangle is the same as the sine of the angle. And what that means is obviously if I adjust the size of the angle, if I make the angle bigger, then y is going to get bigger, so the sine gets bigger. Likewise, if I make the angle smaller, y gets smaller, so the sine of the angle is smaller. But we just need to kind of have a little think about that a little bit further. So I'm going to just jump out to this next one. Here we go. What I've got here is my unit circle again with a slider, so we can see at the moment I've got an angle of theta equals 0, so you can see my black line here, which is the hypotenuse of my triangle. Now I know it doesn't look much like a triangle at the moment, but of course as soon as I start changing the angle, then we're going to see my triangle created. So here we go. So if we start that, we can see that as that red line, which is the opposite side, gets bigger, the sine gets bigger. I'm just going to stop it at 30 there, because what this is telling me now is that this side here has got a length of 0.5 units, and you can see, I said this is going to be the start of my sine curve, so this is effectively plotting all the values for the sine of each angle. So if I keep moving my slide up, we can see that the side gets bigger, so my sine curve increases, so this blue line here is plotting all the values of essentially y equals sine x. And you can see as I start getting close to 90, we can now see that the length of this red line is very, very close to being the length of the hypotenuse. There's very little in between them, because obviously this side's really short, so this triangle here, that side there, is basically the same as that one. And that's why as we get to 90, I can get it there we go. Again, it doesn't look like a triangle, we've just got that red line, but essentially what's happening is the opposite side is sitting on top of the hypotenuse. They are the same thing, so that's why we've got sine of 90 is 1. As we move past 90, what's happening is it's starting to go down again, and you'll notice what we're getting over here. Here's my triangle being created over here, and you'll see that it's going to be symmetrical because the triangles that I'm now creating are exactly the same as the triangles that I was creating in the first one. So I'm going to wind this on to 150. And if you remember, I stopped it at 30, and this side, this triangle here, is exactly the same as the triangle that was over here. See, if that's 150 angle, then this one here is 30. In fact, what I'm going to do is just wind it back. So think about, we've got that 150 angle there. I wind it back. Here we go to 30. I can get 30. There it is. Oh no, there it is. So again, that triangle there, that's the same as the triangle for the angle of 150. Oh, missed it. There you go, 150. So you can see that the curve that's been created is symmetrical. It's starting to come back down again, and as we wind this through to 180. I'll get there in the end. There we go. We're now back down to 0 because the opposite side isn't there anymore. My triangle has effectively just become one line. As we go past 180, you'll see that the curve is now going below the x-axis, so into negative values here. You can see we've got a negative value, and the reason that's happening is if you imagine that on this triangle, these ones up here would be positive, and down here below the axis, this is now negative. So the curve becomes negative, and I'm just going to take it back a little bit, back to 210. There we go. You can see we've got that distance of 0.5. And again, if why have I picked 210? Well, we've got 180 to there, and then that bit there is 30. So again, this is the same triangle as the 150 triangle, as the 30-degree triangle. It's now happening in our third quadrant below the axis, and so we've got a value of 0.5 for our sine, but it's negative. And so you can see what's going to be happening down here is exactly the same as what was happening above, which is why this section of the curve looks exactly the same, but negative again as I get close now to 270. Missed it, there it is. we're back to now we've got a sine of -1. And then as I approach 360, let's stop it at 330. You can probably guess why I'm going to stop it at 330. There it is. You can see there's that 0.5 again. So this section of the curve down here is exactly the same as this section up here, with the difference just being that it's negative rather than positive. And then as I get back to 360, we're back to 0. So there's my sine curve, which is just one complete wave going from 0 up to 90 at 1, 180, 270, and then 360, we're back to 0. So what we should have seen is we've got a sine curve that looks like that. That's just kind of a slightly stretched out version of the one we saw on the previous screen. And we talked about those identical triangles. And so what that means is there's more than one angle that's got the same sine. So for example, if here I'm looking at sine 60, the sine of 60, which is 0.866, there it is appearing in our first quadrant. And if we now look at what's going to happen in the second quadrant here between 90 and 180, you can see that happening. We know that it's going to be the same triangle over there, and so we've got sine 120, it's got exactly the same value. And exactly the same is going to happen in the negative version. So there's my two triangles again, same triangles, but now in the third and the fourth quadrants. So we know that sine 240, sine 300 have got are both minus 0.866, and on the graph we can see them. There they go. There they both are. So what do we know about the sine curve? Well, we've got generally two angles in the range 0 to 360 with the same value for the sine. Now the only exceptions to those are 90 and 270. We've got 90 there and 270 there, but because, let's say, kind of they peak at 1 and -1, those are the only exceptions to that. But you will find that for sine x you can get two angles within 360 degrees that are the same. And what we've got is lines of symmetry at 90 and 270, which is what's going to allow us to work out the value. So for example, if I took sine 47, I know I've got another value between 90 and 180. What is that value? Well, if I know that distance is 47, then this distance here is 47. So all I need to do is go 180 minus the 47, and I know I'm going to get sine 133. So if you wanted to, I prefer to just basically draw a sketch of the curve and just kind of figure it out. But if you want to use that formula, then the simple way to do it is just go sine is 180 minus x. Last thing to note is that this curve, the maximum value point, or the maximum value on here, is 1 down to -1. And the reason for that is, if you think about what's happening, if you think about that circle, it's the hypotenuse that's on the bottom. The hypotenuse will always be the longest side in any right angle triangle. And of course, if you've got the biggest value on the bottom of a fraction, then it's never going to go above 1. So on we go then. Let's have a little look at cosine and tangent curves and see how they function. We'll try and get through these ones a little bit quicker than we did with the sine curve. So here we go. Cos and tan, exactly the same idea. Cosine is the adjacent over the hypotenuse. So that means this time we're doing x over 1. So it's the same length as the adjacent side. So we've got cos theta equals x. And what that means is when we're looking at the curve, let's pick the right one. I think it's that one. There we go. So what we've got now is, you'll see that here's our triangle, or not really looking like a triangle, with that side there being the adjacent side. And because that's the same as cos, that's why this curve is starting at 1. And now, as we increase the angle, the adjacent side is starting to decrease. So that's why the cos curve starts at 1 and then starts to decrease. So what we're saying here is that side there, the adjacent side, that's the same value as the cos. And other than that, it's basically exact same principles before with the identical triangles. Let's just kind of wind it down. So here we go. Going down this, let's go back a bit. As soon as we get close to 90, you'll see now we're getting values of cos that are very, very small. And then we get to 90 degrees, and now effectively the adjacent side has disappeared, which is why the cos of 90 is 0. As soon as we go past 90, we can now see that in this particular case it's now the fact that the adjacent side is in the negative values, because if we take these ones as positive and these ones over this side as negative, so the curve is now negative. And now the cosine is getting bigger because this length of the adjacent side is getting bigger and bigger until we get round to 180. And when we get to 180, the cosine and the hypotenuse, the adjacent side and the hypotenuse are the same length. And so we've got this value here, which is -1. And then keep going. Again, we are getting still negative values, but these values, as we get closer to 270, are getting smaller. And then once we get past 270, there we go. We're now back over here. We're back into positive values for the adjacent side. So the curve has come back into the positive. And as we wind all the way back around, we get to 360. And at 360, there we go. We've got the adjacent and the hypotenuse are the same length. So we're back to 1. So what we've got for our cosine curves, it starts at 1, goes down to 90 at 0, down to -1, and then back up again through 270, and then back to 1 at 360. Right, so going back to it, what that tells us is that for the cosine curve, we've got a line of symmetry, the same as the sine curve, except now our line of symmetry is at 180. So what that means is, if I took, for example, the cos of 47, think about symmetry, that distance is 47, so this distance here is 47, so that means cos of 47 is the same as the cos of 313. Same deal, the values for cos are always between -1 and 1, for the same reason they were for the sine curve. And what we've got is the cosine curve is exactly the same shape as the sine curve, except it's just been translated 90 degrees to the left. So what we've got is the cos of x equals the sine of 90 minus x. So for example, cos 47 is the same as sine 43. So let's have just a quick look at why that happens. Here we go. So there's a right angle triangle looking at theta in the corner here, and we know that sine theta is opposite over hypotenuse. So in this case, that's y over z. Now let's take a look at the same triangle, but instead of looking at this angle in the corner here, let's have a look at this angle up here, which we know has got to be 90 minus theta. If we label our sides, so now that's opposite, adjacent, and hypotenuse, all related to this angle here. So there's my opposite side here, my adjacent side. And you'll notice that essentially now what's happened is the opposite and the adjacent sides have swapped around compared to what we had in the triangle up here. What that means is cos of 90 minus theta is the adjacent over hypotenuse, which is y over z, which is exactly the same as we had up here for sine of theta. So that's telling us that sine theta is the same as cos of 90 minus theta. Okay, so that's the cosine curve done. Now let's just have a little look at what's going on with the tan curve. So let me just quickly jump back to my page. Here we go. Right, so here we go. Tangent, which is opposite divided by adjacent. So what we're looking at here is how essentially that length there interacts with that length there. Now I know this one's a bit more difficult to understand in terms of graphing, in terms of what we've got with these lines here. But if I just say that kind of the fact that this length here is the same as the tangent is to do with kind of similar triangles. I don't think we need to worry too much more about it than that. But the key thing here is just understanding that, let me just wind this back down again. Okay. As I increase the angle, what's happening is the opposite side is getting longer, the adjacent side is getting shorter. Let's just have a look at that. So the opposite side is getting longer, the adjacent side is getting shorter, so we're dividing an increasingly big number by an increasingly small number, which is why the curve is going up and going up quite steeply. If we have a little look at what happens when we get to 45, there we go. What we've got at 45 is the fact that that side there and that side there, because the angle is 45, this triangle that I'm tracing out with my cursor is now essentially an isosceles triangle, so the opposite side and the adjacent side are the same length, which is why the tan of 45 is 1. The real interesting stuff starts to happen when we get close to 90 degrees, and you can see that all of a sudden this line has kind of disappeared straight off the top of the graph, because what's happening is we're getting a longer or relatively longer opposite side, but the adjacent side is becoming very, very short. So what we're doing is dividing by a really small number. And so when you divide by a very small number, what you get is a very, very large answer. And if we can keep winding this up, you'll see now that it's just disappeared right off the top of the graph. If you wanted to kind of take your calculator and stick the tan of 84 into your calculator, you're going to find it's a massive, let's say, getting a much, much bigger number. And when we get, oh, go the wrong way, let's go back to 90 degrees, you'll see the lines disappear, because at 90 degrees what's happening is we've got the opposite side is 1, but the adjacent side is 0. So what we're doing is actually dividing by 0. So at that point we say that the tan of the angle is undefined, because we're doing basically 1 divided by 0. As we get just a little bit past 90, oh no, sliding the wrong thing, try again, there we go. You'll see the dotted line, that's our asymptote, 90 degrees can't happen, and you'll see it's reappearing here, because now what we've got is the opposite side is positive, but the adjacent side is negative. So that's why that's becoming negative, and then, I keep grabbing the wrong thing here, let's go. And as we come down here, what we're finding now is that we're getting closer and closer to 0, because what's happening is the opposite side, this distance here, is getting shorter and shorter, and when we get to 180, our opposite side is 0. So that's why it's at 180. And then keep going, and you can see the same thing's happening again with how the opposite side and the adjacent side are interacting with each other. And when we get to 270, again we've got the same thing as we had at 90, in that the adjacent side is 0, so we've got an asymptote, it's undefined, we're dividing by 0, hence the black dotted line. And then as we get back to 0, we're now here, we've got a situation where the adjacent side is positive, but it's the opposite side that's negative, which is why the tan curve is negative, and back to 360. There it is. So what we get is this kind of slightly bizarre kind of inverted S shapes, that's the blue line, with these asymptotes, the black dotted lines, happening at 90, at 270, and so on and so forth. Right, let's just jump back to my PowerPoints. If we just give it a second. And that's all the stuff we've seen on cos. Right, here we go, moving on. So, tan. What we get is, let's say, this S curve. You'll see kind of this S, kind of inverted S shape here. This is the section that essentially just keeps repeating. If I extended this thing back here, we'd have it happening there. If we kept going past 360, we'd have that S shape there as well. So what we've got is a curve that's very, very different to sine and cos. We haven't got any lines of symmetry, and we've got those asymptotes at 90 and 270, where we say that the value of tan x is undefined. And what we've got is these separate disjointed kind of S shapes, and they just kind of shift along by 180 degrees each time, which basically means if I take tan of 47, the next value I'm going to get for tan with the same as tan 47 is 180 degrees further along. So that's going to be 227. And if I wanted the next one, just keep adding 180. So rather than using symmetry, all we're doing is just kind of adding multiples of 180 for tan. Final thing to talk about is negative angles. What do we mean by a negative angle for tan? For sine, cos, or tan. So here we go. Negative angles. Basically what we've got is positive angles are measured in an anti-clockwise direction. So theta on my diagram there is positive. And then negative is simply measured in the opposite direction. So negative angles are measured clockwise. And so if I had a value of theta there, it would be minus 34. That would be exactly the same as that angle there that's now appeared in my diagram. So that would be the same as positive 326. So those two angles are two ways of describing exactly the same angle. Just one with a negative and one would be a reflex angle. Additionally, if we kept going and went beyond 360, we could see that kind of if we went to 360 and then went another 34 degrees beyond that, that would be 394 degrees, and so 394 is the same as 34. And so all my curves just repeat in 360 degree cycles. So you can see there for tan, we had our original graph going from 0 to 360, and then the same thing again, that tangent is happening again from 360 to 720, and it's happening again from 0 to minus 360. So all that's happening is just these, and the same happens for sine and cos, they just repeat every 360 degrees. So if, for example, I knew that the tan of a particular angle was 2, then that would give me my first angle, which would be 63, but that would also then give me 243, add another 180, 423, add another 180, 603, going back into the minuses, we'd have minus 117, so that one is 63 minus 180, and that would be minus another 180 degrees again. So there's no reason why you can't just keep going with these angles beyond 360 to into the positives as far as you want to go, or negatives as far as you want to go.